Every financial transaction, every streaming video, and every global communication flows through server farms like this one. This infrastructure is the backbone of the modern world. The fundamental unit driving this power is the binary bit, which represents information as a strict choice between a 1 or a 0. This forces computers to process information linearly, calculating one step and then the next in a single file sequence. But we have reached a processing wall. When we try to model systems with millions of variables, like global logistics or molecular biology, the number of possible outcomes grows too large for a linear machine to handle in a reasonable timeframe. To solve these problems, researchers are looking to the subatomic world, where particles do not follow a single linear path. By building a computer that mimics this behavior, we can move from testing one calculation at a time to evaluating every possible outcome simultaneously. Transitioning from binary logic to subatomic control is a massive engineering hurdle. Mastering these forces requires a total redesign of how we build hardware, shifting the goal from faster bits to stable quantum states. Zooming past the circuits into the microscopic void, we leave the standard bit behind. Here, the foundation of processing is the quantum bit, or qubit. While a classical bit is a static switch, this qubit operates in superposition. It exists in a fluid state, occupying all possible combinations of 1 and 0 at the same time. When two qubits are entangled, their states become linked. A change to one instantly dictates the state of the other, regardless of distance, working as a unified system. Scaling this up creates a massive computational web. This interconnected grid enables quantum parallelism, where the system evaluates thousands of distinct processing pathways in the same moment. This architecture allows the computer to navigate an entire maze of data at once. It finds a specific solution in seconds that would take a classical machine, calculating one path at a time, thousands of years to reach. While these subatomic mechanics are powerful, they are incredibly difficult to maintain in a physical environment. Qubits are sensitive to the smallest amounts of energy. A microscopic spike in heat or a stray electromagnetic wave causes decoherence, where the quantum state collapses and the calculation is instantly destroyed. To prevent this sudden collapse, engineers build extreme cryogenic environments to perfectly shield the delicate hardware from any external interference. This dilution refrigerator uses specialized helium isotopes to strip away heat across multiple levels. At the final tier, the temperature reaches near absolute zero, colder than deep space, to freeze out the environmental noise that would otherwise break the quantum state. This is the central challenge of the field. The very subatomic flexibility that allows for high-speed processing also makes the system so sensitive that it requires total isolation to function. These concepts are now moving into physical reality. Companies like IBM are operating modern labs where massive gold-plated dilution refrigerators house the first generation of quantum hardware. Inside these systems, engineers are deploying advanced processors like Nighthawk, which are designed to increase the number of stable qubits that can be managed on a single chip. To make these chips reliable, researchers use a system of watcher qubits. These secondary particles run error correction algorithms to catch and neutralize interference before it can spread through the main data qubits. Developing these fault-tolerant systems is the final requirement for moving quantum computing out of the laboratory and into industrial use. Once stabilized, these machines will target specific industries that are currently slowed by complex math. In global logistics, quantum systems can untangle thousands of shipping variables to find the most efficient route instantly. This shift from linear to parallel processing allows for a level of optimization that traditional computers simply cannot achieve, regardless of how many servers we add to the grid. In medicine, these systems can simulate how new drug compounds will interact with human cells. By calculating every molecular combination in a simulation, researchers can identify successful treatments without years of trial and error testing. This speed also changes the landscape of data security. Most modern encryption relies on the fact that classical computers take centuries to factor very large numbers. A quantum system can find those factors almost instantly, rendering standard digital locks obsolete. From chalkboard theories to physical hardware, quantum computing has reached a functional milestone. It is no longer just a physics experiment, but a tool that changes how we simulate, secure, and move the world around us.